the subject matter of these lectures is exact signal recovery. So I discussed this yesterday, but let me give you a quick overview. So what is the basic problem? Also, let me mention that you should interrupt me anytime for any reason. Okay? I like questions. In fact, as I said yesterday, if you want to make me happy, you should ask me at least 2 questions. If you don't have a question, make one up. Okay. So what is the basic idea? So you have a signal F, and a signal is what engineers insist on calling functions from Z and D to complex numbers. And suppose that the Fourier transform of this signal is transmitted. Okay? And this is just a standard discrete Fourier transform over Z and D. So Z mod n is integers modulo n, and Z and D is a d-dimensional grid over integers modulo n. Okay? So standard Fourier inversion formula tells us that we can recover the function or the signal from its Fourier transform. So if the whole signal gets through, if the whole Fourier transform gets through, then we can recover the signal exactly, and we can decode the message. But the subject matter of these lectures is what happens if some of the signal is lost. And signals can be lost due to a variety of reasons, interference, noise, etc. Okay? And the question is, under what reasonable conditions can we still recover the signal exactly and uniquely, given that some of the frequencies are lost? So this is the subject matter of these lectures. Okay? So the main tool in the study of this problem is the Fourier uncertainty principle. Okay? And the Fourier uncertainty principle says that the size of the support of the signal times the size of the support of the Fourier transform is bounded from below by the size of the space. Okay? And so some of you were not there yesterday, so I'm going to just give you a quick review of some of the main ideas involved. So I'm going to fast forward to the method that was developed by Donahoe and Stark and Matolchi and Jukes. So this is a story that I told yesterday. So there's a beautiful paper by Donahoe and Stark published in 1989, very influential paper. But one of the main results in that paper was published in 1973. And as I like to say, half jokingly, in the US, we don't like learning foreign languages. That paper was published in French and it somehow flew under the radar, even though both authors are quite prominent mathematicians. All right, so let me describe the method of Matolchi and Jukes. Okay, so what is the general idea? So as I said, if you have a signal from Z and D to complex numbers, then the size of the support of this signal times the size of the support of the Fourier transform is bounded from below by n to the d. The proof is very simple and very well known. And the same argument works on any locally compact abelian groups. Even in Euclidean space, where there are complications, the proofs tend to be not very difficult. Okay? So suppose that you have a signal and which is supported in a set E, and frequencies in S are unobserved. Okay? So what does it mean that we cannot recover that signal uniquely? What it means is that there exists another signal G, okay, which has support of the same size as the signal F, and the Fourier transform of F and the Fourier transform of G agree, except on the set of missing frequencies. We can't talk about the set of missing frequencies because we don't know what's going on there. And F doesn't equal to G. So this is what it would mean for the signal not to be recoverable uniquely. So we take H to be F minus G. Since Fourier transform of F and Fourier transform of G agree away from S, F minus G Fourier transform is supported in S. On the other hand, since H equals F minus G, the support of F, the size of the support of H, is at most twice the size of the support of F. Okay? And by the uncertainty principle, we get the equation. The size of the support of F times the size of S is bounded from below by n to the d over 2. Okay, so what do? We simply invert this inequality. If we assume that the size of the support of F times the size of the support of S times the size of S is less than n to the d over 2, then laws of nature are violated. What does that mean? It means that H is identically 0, and that means that the signal is recoverable uniquely. So this is the Bartolczy-Żuk's-Danaher-Stark method. Okay, please.
It helps the size of the support, but we know the support.
If you know the support exactly, sorry, then you don't need to lose this factor of 2. That's the only thing that changes, right? Because you don't have to move around.
Still, standard different factors.
Yeah.
But that give some extra information to use to sharpen the inequality.
No, it cannot give information to sharpen the inequality because they're sharpness examples. But what it does is, so where it makes a difference is in the realm that I'm not talking about so much in these lectures, namely the recovery mechanism. So suppose you wanted to recover the signal in the most naive possible way. Then if you only know the size of the support, you would have to consider all possible signals supported in a set of that size. But if you know they're supported in a given set E, then your algorithm becomes much, much faster, right? Because it takes exponentially long to sort through all the sets of a given size. Okay, so it doesn't improve the result, but it improves the recovery algorithm. Okay, and so let me also quickly mention that in general, the uncertainty principle is sharp. So the example that I give here is when n is an odd prime and S is a k-dimensional subspace. Then the Fourier transform is up to a constant multiple, the indicator of an orthogonal subspace, and you see that the uncertainty principle is sharp. If n is composite, you can still consider subgroups, and the Fourier transform is supported on the annihilator subgroups. Okay, so once again, you can see that the uncertainty principle is sharp. But largely, the point of these lectures is to show you that for a typical set S, one has a much better uncertainty principle. In other words, the situation where the size of spatial support times the size of Fourier support is only bounded below by n to the d is what we call in English a man bites dog situation. Okay? It very, very seldom happens. Okay. So in particular, we're going to see that in the presence of the so-called non-trivial restriction estimate, and I'm going to explain what that is, one can always do better. One can always get a better uncertainty principle. And consequently, one can always get a better recovery condition. And furthermore, we're going to see that such estimates, such non-trivial estimates, typically hold. So in a typical situation, for example, in a situation where the lost frequencies are random, one can always do much better than the Danaher-Stark Bartolczy-Żuk's result says. Okay? Is everybody with me? Life is good? Okay, so it's a beautiful sunny day. It's a great day to talk about mathematics. But then again, any day is. All right. All right. So let me skip through the proof of the uncertainty principle. So here is a result that is joint work with Karam Aldalay, Joshua Iosevich. Yes, he's related to me. Jay Mangal, Azita Mayeli, and Svetlana Peck. So this has to do with an experiment that I started running a couple of years ago, and that is involving very strong undergraduates in serious research projects, not just toy research projects, but serious research projects. And these are very, very bright students. And so last summer, we produced the following result. So first, let me give you a definition. So additive energy of a subset is defined as the number of quadruplets, x1, x2, x3, x4, so that x1 plus x2 equals x3 plus x4. Okay? So notice that the size of energy is always at least 3 times the size of A squared. Okay? Because there's always the case where x1 equals x3, x2 equals x4, or vice versa. And if 0 is in your set, there's always the case where x1 equals minus x2 and x3 equals minus x4, right? And at most, the size of the energy of a set is the size of the set cubed, because we can always fix 3 of the values and solve for the 4th. Okay? And you can easily check that if your set is a plane, then it has the worst possible energy. You can also check, though it requires a bit of a calculation, that if you're, let's say, in 2 dimensions and n is prime, and your set is a parabola or a circle, then it has the best possible energy. A parabola is even better than a circle. The constant is 2 instead of 3.
But I am doing this smaller.
Best, oh no, best is smaller. Okay. Okay, of course, this is a value judgment, but to me, it's the best when the energy is low, because the set is more chaotic, and I always prefer chaos. Yeah. Okay. So as I said, this quantity measures the extent to which a given set is arithmetically closed, or approximately arithmetically. Okay. All right. So here is a result which indicates how one might be able to improve. I'm going to give you several such results in various reincarnations about how one may be able to improve the classical uncertainty principle. Okay, so here again, F is a signal. It's supported in E, and the Fourier transform is supported in S. Okay, and so this time, instead of having the size of E times the size of S being bounded from below by n to the d, we have the size of E times this quantity that I consider quite cute, but this is a matter of opinion. It's a maximum over all the subsets of S of the size of additive energy of U divided by the size of U squared. And you can take this quantity to the power of alpha and multiply it by the same quantity where the rows of E and S are switched. So we can take advantage of the set S being very irregular, and we can also take advantage of the set E being very irregular. Typically, in signal recovery, the focus is on S, because you send a message, and the message is supported in E. And so you typically don't control the message. You want to be able to send every possible message. Whereas the S is the set of frequencies that are lost, and it is reasonable to assume that they are random. Nevertheless, this result allows us to take advantage of structure or lack of structure in both E and in S. Okay? So here, one example to keep in mind. So first of all, since lambda of U is always less than or equal to the size of U cubed, as we discussed a moment ago, this certainly implies the classical uncertainty principle. Okay? And so whenever the energy set of F for every subset is little o of the maximum of the size cubed, then we get an improvement on the uncertainty principle. Okay? So let me give you an example of where this gain is particularly clear. Yeah. Oh, it should be the size of F cubed. Okay. As I mentioned yesterday, the error correction process doesn't converge, because when you correct errors, you introduce new ones. Okay. I fixed all the typos from yesterday. I think there are only 2, but still. Right? Huh?
Serious about this.
I recognize the humor of the situation. It's not entirely unintentional.
Sigma. Yes.
Yes. Yes, I couldn't. Oh, so the explanation for this is very simple. I prefer notation capital S for the set of missing frequencies. My co-author, Azita Mayeli, prefers capital sigma. And so we tend to alternate in various papers.
Now you know which parts are written.
Uh, sort of, yeah. Yeah, actually, pretty much, yeah. Okay, so here's an example. Suppose that n is an odd prime and dimension is 2, and let S be a circle. Okay, so here comes a property which has been familiar to us since we took high school geometry. Actually, in the US, geometry is taught in high school less and less often. I hope that this problem is not happening here. You should fight tooth and nail. You should keep this from happening. Anyway, all right. So, and here it's very easy to check that the only way the equation m plus L equals m prime plus L prime could hold is if m equals L, m prime equals L prime, the reverse of these, or if m equals minus L and m prime equals minus L prime. This is elementary geometry. But one thing that I don't remember realizing when I took geometry, yes, of course, it was a long time ago, but I don't remember realizing is that it's not a, is that it's purely an algebraic property. It doesn't really require geometry. It follows in a few lines from the equation. And this implies, yes, sir.
S for not geometric circle because there is no geometry there.
No, there's no geometry here, but that's precisely my point, is that if there were geometry here, it probably wouldn't be true, right? But it's, uh-huh. There's no curvature, right? There's geometry as we are demonstrating, right? There is geometry there, but it's not, it's that the standard geometric intuition may or may not hold in this context. In this case, it does. Okay? But if n is not prime, the intuition that we have collapses in a spectacular way, depending on the number of prime divisors, etc. Okay? But nevertheless, if you take a maximum over all the subsets of the energy of U over the size of U squared, then this is simply less than or equal to 3. And that tells us that if F is supported in E, and the Fourier transform is supported in this circle S, then in fact, the size of E is a positive proportion of the whole space. It's at least n squared over 3. Okay? As we're going to see later, this is not as surprising as it looks, but nevertheless, it's an immediate and clear improvement over the classical uncertainty principle.
Do you know how large this S is?
Oh, sure. I'm sorry. So we're in a prime case. If n is congruent to 1 mod 4, then the size of the circle is n minus 1. Because if n is congruent to 1 mod 4, then square root of negative 1 exists, which means that the zero circle, speaking of geometric intuition, the circle of zero radius has 2 n minus 1 points, right? And all the other circles have the same radius. If n is congruent to 3 mod 4, this is the only remaining case. Then the square root of negative 1 does not exist. And that means that the zero circle consists of 1 point, thank God for small favors. And that means that the size of the other circles is n plus 1. Okay? So the moment you lose primality, none of this is true. And it's a fascinating subject, but it's not something that we're going to discuss today. So what did I promise? I promised you a mechanism that would allow us to improve a sort of a consistent mechanism that would allow us to improve the uncertainty principle and hence the recovery condition for the signal for a typical set S. Okay? Let me also slightly put this into context. There's a variety of results, some of which I may mention by the end of today's lecture, which give you improved recovery conditions for random sets. But we have already seen that for something that is very deterministic, like a circle, one can still get improved results. So the purpose of restriction theory, so this was our goal with Zita Maeli, is to create a mechanism which incorporates both deterministic sets like circles that have good energy bounds and random sets which always have good energy bounds in a single mechanism. Okay, so these lecture notes is a result of a year-and-a-half long effort to unify random and the so-called pseudo-random cases. All right, so what is a restriction estimate? So we say that S in Z and D satisfies a PQ restriction estimate with norm CPQ if the following holds. So you have the LQ norm of the Fourier transform restricted to S, and we normalize by the size of S. It's a probability measure. And this is bounded by the norm times n to the minus d over 2. This is due to the normalization of the Fourier transform times the not normalized LP norm of F. Okay? So whenever you see things like this for a first time, you're surely asking yourselves, why this particular normalization? Why am I looking at this, right? And one way to see that this is probably the right normalization is to notice that when p equals 1, this inequality always holds, and it always holds with norm 1. So why is that? Because the modulus of the Fourier transform by the triangle inequality is bounded by n to the minus d over 2 times the L1 norm of the function. Okay? Since the left-hand side is the average, this filters through, and you immediately get a bound by the right-hand side with constant 1. Okay? So a restriction theorem always holds when p equals 1, which means that if I were to tell you that I can get an improved uncertainty principle based on p equals 1 restriction theorem, I would be lying. So the only way one could even potentially improve the classical uncertainty principle is to obtain such a bound with p greater than 1. Okay? Now, one thing to keep in mind, and I stressed this yesterday, and let me stress this again. You should think of capital N as being large, but everything is finite, which means that what we mean by a non-trivial estimate is where CPQ is a number like 5 or 10. And N, as I like to say, is at least the size of the American national debt.
It's not mixed.
Oh, no, it's a rapidly growing quantity. Yeah, both political parties make sure. Yes. Okay, and here's a result that illustrates, that gives you a perspective on these estimates. And this is a so-called universal restriction theorem. What we mean by universality is that it's a theorem that doesn't require assumption. It works for all non-empty sets F. Okay? Of course, whenever you have the result like this, it does not mean that the bounds that you get are good for every possible S, but it is universal. No matter which S you plug in, you get a result. So if you compare the theorem with the line above, you'll see that n to the minus d over 2 is present in both places, right? Which means that you should think of this quantity before n to the minus d over 2 as the constant CPQ. Okay? So whenever that quantity is good, you get a good result. And let's just eyeball it. When is that quantity reasonable? It is reasonable when, let's say that the size of S is approximately n to the d over 2. Then the first term disappears. Okay, well, I mean, by disappears, I mean it's approximately 1. And suppose that U is a set like, that S is a set like the circle. Then the second quantity is good. And then you get a nice restriction theorem from 4/3 to 2. This is just one example. I'm certainly not saying that this is the only situation in which this bound is good. Please.
Is the constant 4/3 very important for this now.
It is important if you use energy as I defined it. So the notion of energy that I defined is x plus y equals x prime plus y prime. If you're willing to consider x plus y plus z equals x prime plus y prime plus z prime, then 4/3 becomes 6/5, and et cetera, right? But I'm very happy that you asked this question, right? Because it can't be that the future of signal recovery relies on the number 4/3. That just doesn't make any sense, right? This is what you're thinking, and you're correct. In a few minutes, I'm going to give you a much more general mechanism based on Jean Bourgain's celebrated lambda p theorem. But what I want to indicate is that if you just want to see that there is an improvement for general sets, you can already see it here. Because if you choose the set S at random, you're going to get better than trivial estimate, even based on this relatively primitive result. Okay, although calling it relatively primitive is perhaps an overstatement, this is a discrete manifestation of Charles Pfefferman's proof of the Buckner-Rees conjecture in the plane. So this is his 1973 paper. And if you look at the proof of this result and Pfefferman's proof of the Buckner-Rees result, it might take a while before you realize it's the same proof. Because analysis tends to be ugly. You have to deal with Gaussian tails, you have to deal with approximations, et cetera, et cetera. But the core idea is the same. Okay, this is one thing that Pfefferman was always incredible at, is coming up with a simple idea and then pushing it through the technicality. Okay. All right. So before proving the universal restriction theorem, we're going to develop a simple mechanism for going directly from restriction to uncertainty, where the more non-trivial the restriction estimate becomes, the better uncertainty principle we obtain. Okay? I'm going to give you a more elaborate approach a bit later, but I just want you to see it in its original form. First of all, this approach works better with concrete applications, which I'm unfortunately not going to get to today, but in terms of time series analysis. But also, this approach is near and dear to my heart because this is the approach that Azita Mayeli and I came up with in the first hour of working on this problem. So this is how it all began. All right. So this is the theorem from last year. Suppose that f and f hat are signals from Z and D to C. F hat is the Fourier transform. F is supported in E, and f hat is supported in S. Okay? Suppose that S satisfies the PQ restriction estimate with norm CPQ. By the way, I'm going to prove the universal restriction theorem a bit later. Okay? Then you get that the size of E to the 1 over P times the size of S is bigger than or equal to n to the D divided by the norm of the restriction operator. So first of all, I promised you that the P equals 1 restriction always holds with constant 1. And if that happens, you simply recover the uncertainty principle, right? So mathematics works. We did not discover any contradictions in foundations of mathematics, which is always nice. Okay? But if P is bigger than 1, and CPQ is some concrete constant, and capital N is huge, then we get a clear improvement. Right? Mm-hmm. And so let's go ahead and prove the uncertainty via restriction. It is very, very simple. Read.
The engagement P equals 1.
No, it equals 1.
If P equals 1, then CPQ equals 2.
No, if P equals 1, CPQ equals 1. Absolutely. Just take a look. So just take a look at the formula above. Dominate the modulus of the Fourier transform by n to the minus d over 2 times the L1 norm above. It's just a triangle inequality. But the left-hand side is an average, so it will hold for any Q. Yeah, so the constant is 1.
So it's well, you take the smallest possible.
Right. This is why I refer to it as a norm, although as you know, in real life, finding the best constant, you're much more likely to get hit by lightning 3 times. Find the best constant. It's a nasty business. Right.
But you just found one. You just found one.
So that's the case of lightning hitting, yeah, absolutely. But, you know, finding best constants is very, very hard. It's very beautiful when it happens, but it's very hard. Okay. All right. So we write the function as an inverse Fourier transform of its Fourier transform, except that it's enough to sum over M and S because of the support condition. Okay? And by Holder's inequality, modulus of f of x is bounded by n to the minus d over 2 times the size of S times the normalized LQ norm of the Fourier transform over f. Okay, this is literally an exercise in Holder's inequality. Okay, when I teach graduate classes, I occasionally encounter students who believe that Holder's inequality can only be applied to integrals, but it's okay. I just go have a drink of water, I come back, and everything's fine. Yes. But that's the thing, is that in the American educational system, we teach integrals before we teach sums. The stupidity of this is unfathomable, right? It's right. Basically, I would have never become a mathematician if my father had not given me this Hungarian encyclopedia of mathematics when I was young. This is the only thing that saved me. It is remarkable how many mathematicians the United States produce given our educational system. It's a miracle. Okay. No, no. Some of them are produced in the same. I mean, yeah. I mean, Charles Pfefferman was born in New Jersey. I mean, you know, it happened. Okay. So, all right. So now we applied the restriction bound assumption, and so by assumption, this is bounded by n to the minus d over 2 times the size of S times CPQ. There's another n to the minus d over 2. So now it's n to the minus d. And now we have a pure LP norm of F. Okay, so far so good, right? So far, this is all elementary school mathematics, right? Okay, this is the level at which I prefer to operate. And by the support assumption, we can restrict the LP norm of F to E. Okay, fantastic. So if we put everything together, modulus of f of x is bounded by the size of S, CPQ, n to the minus d times the LP of E norm of F. Okay? Now we raise both sides to the power of P. We sum over E. This introduces size of E on the, well, here on the left-hand side. And now we divide both sides by the LP norm of F, which we can do because if this LP norm is 0, then there's nothing to discuss. And we recover the condition. So this is it. So this, okay, there's a much more sophisticated mechanism that I'm going to introduce, but this alone tells us that that in the presence of any non-trivial restriction estimate, and we have seen at least hints that this typically happens because all you need is non-trivial energy, and non-trivial energy is certainly a typical situation because if you choose a set at random, there's absolutely no reason why this equality should hold, except in trivial cases. If the set is small. If the set is larger, then you have to do a tiny bit of combinatorics, right? Okay, so this completes the proof of the first uncertainty principle via restriction theory, okay? So now let me prove the universal restriction theorem. So I remember reading Pfefferman's argument when I was a student, and this is when I realized that I have to study harmonic analysis, okay? Because even though, like I said, if you look at his paper, this is not what you're going to see. That's his argument, okay? So you take the L2 norm of the Fourier transform squared, and you simply write it out as the summation over M of the indicator of S, F hat of M, G of M, where G of M is the same thing with a complex conjugate. And why do we do this? We do this because, we all took calculus once upon a time, and we all got excited when we had this integral of e to the x sine x, and it was solved by integrating by parts twice and solving for it in terms of itself. That's what we're going to do here. Okay? So what is this expression equals? We simply write out the Fourier transform of f, and we change the order of summation. And as I said yesterday, you should never call it Fubini because it's a finite sum, and you should not use Fubini's name in vain. Okay, and you get summation over x of f of x, and then indicator function of s times g, Fourier transform at x. Okay, so we just recycled the Fourier transform. Now we applied the L4 thirds to L4 Holder's inequality. And at this point, you should be asking yourselves, why L4 thirds L4? There are other exponents. But the point is when you take the L4 norm of the Fourier transform, this is precisely when that additive energy condition appears. Okay, so this is what Pfefferman noticed. Okay, and okay, Pfefferman didn't notice this. Klaus Roth got a Fields Medal for this in 1953, but he noticed it in this context. Actually, I just realized that Hermann Weyl used he celebrated exponential sum estimates were in 1915. So it's the usual thing. There's nothing new under the sun. Okay. All right. So we write out, let's take the L4 norm of the Fourier transform to the power of 4 and write it out. So it's n to the minus 2d. Then we have 4 copies of the function g. And then we have a summation over x of chi of m plus l minus m prime minus l prime dot x. Okay, now you know what? There's a point. Okay, so that's typo number 2. Excellent. Okay, this is good. Like I said, doesn't converge. And now, when we sum, right, we get 0 unless m plus l equals m prime plus l prime, in which case we get n to the d. So then we are here. Okay? So here, what I'm going to show you is a proof of a slightly simplified case where g is an indicator function of a set. But if g is not an indicator function of a set, it's a triviality because we're in a discrete context, you can write any function as a linear combination of indicator functions and everything works out. It's literally impossible to go wrong. Okay? It really is. So in analysis, of course, we have beautiful theorems about this, and you generally miss the endpoint. Here, you don't miss the endpoints. Everything works out cleanly. There are no tails. There are no issues. Right? There's no complicated interpolation theory. Okay. And so this quantity, for that reason, so this is why you have this maximum over subset, because G could be an indicator of any subset of S. So this is bounded by n to the minus d, maximum over the subsets of lambda of u over the size of u squared, times the L2 norm raised to the power of 4. So as I said, it's clear for indicator functions, and then you just do a tiny bit of algebra. Okay? And it follows that the L4 norm of the Fourier transform, 1SGX, is bounded by n to the minus d over 4, this quantity maximum of lambda u over norm u squared to the power of a quarter, and the L2 norm of g. But what is L2 norm of g? L2 norm of g is the square root of the quantity that we started with. Okay? So this is just an iteration argument, right? So we put everything together, and we get that the normalized L2 norm is bounded by n to the minus d over 4, then the energy quantity to the power of a quarter, size of S to the minus a half times the L4 thirds norm, and the rest is simply bookkeeping. In fact, it's really a matter of taste in what form you write it. Okay? And this is how sort of classical Pfefferman's argument plays out in this case and gives us a universal restriction here. Okay, so this completes the proof of the universal restriction theorem. So are the time parameters same as yesterday?
Just over 6 till 6:35.
Oh, six. Oh, perfect. Perfect. This is wonderful. Okay, I don't have to hurry or anything. Okay. So, okay. So now let's prove the additive energy uncertainty principle, right? But at this point, maybe it's not so easy to remember what it said. So let's go back to the additive energy uncertainty principle. Okay. It's that if f is supported in E and the Fourier transform is supported in S, then for any alpha between 0 and 1, the size of E times this energy quantity that we've been talking about to the power of alpha times the size of S, again times the energy quantity, but now for subsets of E to the power of 1 minus alpha is bigger than or equal to n to the d. Okay? So this is I think that there's a cute pedagogical point here. Of course, it's enough to prove this with, let's say, alpha equals 1. Of course, the word of course is a dangerous word, right? So why is it enough to prove it for alpha equals 1? Because by reversing the roles of E and S, so Fourier transform is an order 4 operation, not order 2, but for all practical purposes.
Right.
Oh, it's even less than that. It's even less than that. No, I mean, that would work, but we don't need it, right? Because you take alpha equals 1, and you prove it, and I'm going to do this in a moment. That immediately implies the case alpha equals 0, and then it's just a, so okay, so it's just a convex combination, just really.
Yes. One can say, think that you see like a pop on the edges of the place around there. You take out, so the main size bar still depends alpha, and if you take out everything to the power of alpha.
So your point is that the case alpha equals 1, alpha equals 0 are the only ones that actually matter. Yeah, I think you're right.
That's not sure what you can guess. Then
No, I will think it through afterwards, but I think he's right that that the case when alpha is between 0 and 1,
it's some.
yeah, is suboptimal. It cannot be measured. Okay, in any case, we're going to prove alpha equals 1 and alpha equals 0. We're going to get by the grace of God. Okay, and let's go. It's a good point. Yeah. Okay. All right. So yeah, so this we already know. Okay. So proof of the additive energy uncertainty principle. So we take the weighted L2 norm of the Fourier transform restricted to S, and we apply the universal restriction theorem. So we simply write it down. Okay? And it follows that's just the L2 norm over S is bounded by, we simply take out the size of S to the power of 1/2. Okay? Yes. So today's lecture is more technical than the one yesterday, but mathematics is like that. Okay. And
Just multiplying through.
just multiply. There's nothing happened here. Okay. So since the Fourier transform is supported in S, we can apply Poincaré. Okay. And here, Poincaré really, really scores. And then you can immediately restrict it to E because by assumption it's supported in E. And then just a regular L2 norm of F is bounded by the size of S to the 1/2, the size of S over n to the d over 2 to the power of -1/2, our favorite energy quantity to the power of 1/4, n to the minus d over 2, and the L4/3 norm. Okay? So now we apply Holder. And so this is a simple idea that you're going to see over and over. Is we need to balance the L2 norm, so we're going to bootstrap up to L2. So the L2 norm of F is bounded by the size of S to the 1/2, the size of S over n to the d over 2 to the -1/2, our favorite energy quantity to the power of a quarter times the size of e to the 1/4 n to the minus d over 2. But now we have L2 norm of f. So the extra factors that you see just come from bounding the L4/3 norm by the L2 norm. And since it's not a probability measure, you have to put in factors. Okay, awesome. So what have we just shown? We've just shown that n to the d over 4 is bounded by the energy quantity to the power of a quarter times the size of e to the 1/4. We raise both sides to the power of 4, and there we go. And that's the end. Because, right, it's not by the same argument. So what I wrote, it's exactly by the same argument. It's less than that. It's simply by reversing the roles of E and F. Because it's what, it's what one of my undergraduate professors called proof by the grace of God. It was Arunas Lulovich, she's a apologist. Okay? So you get the same argument, and then you can take a convex combination, though I think that Alexander is right, and there's no point taking a convex combination. I think you always get something that's worse. I'll think it through just in case. Okay? Life is good. So again, I'm aware of the fact that this material is technical, but I'm trying to keep it as I'm trying to keep the level of technicalities to a minimum. All right. So here's another version of the additive energy uncertainty principle. And it would be very nice to have a version that relied only on energy of E and only an energy in S. Because mathematically, this quantity where you take the maximum over subsets, it looks cute. From a practical point of view, how are you going to compute that ever, unless you have a circle or something, or a random set? So here's another version. This is, again, joint work with the same group of people. So Svetlana Peck just started a graduate program at Penn State. You will hear that name, I promise you. Okay. So F map Z and D to C was support of F is E, and support of the Fourier transform is S. Then for any alpha in 0, 1, you have n to the d is bounded by the energy of E to the power of alpha over 3 times the energy of S to the power of 1 minus alpha over 3 times the size of E to the power of 1 minus alpha times the size of S to the power of alpha. And once again, so take alpha equals 0, take alpha equals 0, then you get energy of S to the power of 1/3 times the size of E. The energy of S to the power of 1/3 cannot possibly be larger than the side of S, even in the most trivial possible case. So once again, you recover the classical uncertainty principle. But what this shows, and I think in even more clear way than the previous result, is that any gain, in other words, if the energy of either E or S is better than the trivial, you instantly get a better uncertainty principle. Okay, so in some sense, I think this formulation is more useful. Okay, and let's go ahead and prove it. There's a cute little twist here. So again, you write F in terms of its Fourier transform. We've seen this a million times. We'll see this a million more times, especially if you watch the Kiev lectures. Okay, and so we again, but this time we go straight for the 4/3 for Holder's inequality. And now we are no longer asking why it's L 4/3 4, because we know we want energy of energy to come up, right? Okay. And so we take the L4 norm of the Fourier transform of F, and we bound this. We again have this quantity. Oh, I think I have parentheses, correct parentheses this time. Okay. Okay, thank God for small favors. Okay. So we have chi of x plus y minus x prime minus y prime dot m. You have 4 copies of F. And if you sum in M, you again, this condition that you're summing over x plus y equals x prime plus y prime. And now x, y, x prime, and y prime are in E. So what is going on? The function F is getting in the way. So what happens when things get in the way? You bound them out. So what is the most trivial way of bounding it out? L infinity norm. So this is bounded by n to the minus d times the energy of E times the L infinity norm to the power of 4. So, okay, so this is all well and good, but can we get away with this? And we can. Okay? So you put everything together and you see that the modulus of f of x is bounded by n to the minus d over 2 times the size of s to the 3/4, n to the minus d over 4, lambda to the quarter of E times the L infinity norm. But now you see the point. There's L infinity norm on both sides. And you can cancel L infinity norms just as well as you can cancel L2 norms or L1 norms. Okay? And so you take a maximum, you cancel, you get n to the 3d over 4 is less than or equal to lambda to the 1/4 of E times the size of s to the 3/4. Or equivalently, you get n to the d is bounded by lambda to the 1/3 of E times the size of s. And as I said, by the grace of God, you get the same thing with E and S changing roles. Okay? And this completes the proof. Then we can take a convex combination, and I will think about whether taking a convex combination, as we used to say in the old country, advances the cause of socialism. Yes. Anyway, that's the joke. Okay. All right. All right. So let me look at the time. It's 5:37. You said I have until when? 20 minutes. Perfect. Perfect. Oh yeah, I'll leave some time for questions. Yeah, no, of course. Time for questions, for time for people to throw tomatoes. Yeah, absolutely. Okay. And okay. So one of the greatest theorems by one of the greatest mathematicians of the past 100 years, Jean Bourgain, is the following beautiful result. So suppose that G is a locally compact abelian group. I did not believe the statement when I first read it. Okay, so suppose that G is a locally compact abelian group, and phi1 through phi(n) are any orthogonal functions, any, with L infinity norm bounded above by 1. Okay, and then for a generic set S in 1 through n, generic here simply means that you choose it randomly, so that the expected size of the set is approximately n to the 2 over q, for some q bigger than 2. So for any generic subset, you have the LQ norm bounded by the L2 norm with a constant that only depends on Q. Of course, the L2 norm is always bounded by the LQ norm because Holder's inequality is still in effect. But this goes the other way. So this is really one of the most fundamental theorems in Fourier analysis as far as I'm concerned. Okay? And what I'm going to try to convince you of in the next few minutes, and this is probably the last thing I'm going to do, is, sorry.
It's not a great hearing this.
Pleasure.
So is it another result on using at least in continuous case, it's about Fourier series.
Right, right. That's true. You recovered that in the continuous case. So this is not the, yeah, QQ is larger than 2. The point is you take a thin subset. Okay, so it's hard to think in the realm, okay, I have friends who are able to visualize locally compact abelian groups. For me, it needs to be concrete. So this will make much more sense, I believe, once you see this particular manifestation of Bourgain's result. So here, okay, I call it lambda p theorem because Bourgain called it lambda p. For us, it's lambda cube, but letters are letters, as long as they're used consistently. So if f is a signal from Z and D to C, and the Fourier transform is supported in S, which is a generic set of size approximately n to the 2d over q. Okay? So that's the same as little n to the 2 over q, because our space has size n to the d. Then weighted LQ norm of f is bounded by the weighted L2 norm with constant KQ of S independent of n. Okay, so this is what Bourgain's result says. And what I'm going to describe is that this result has a simple and powerful uncertainty principle built in. Okay. Also, please note that this is also a restriction theorem, or more precisely, it's an extension theorem. Right? It's a dual of the restriction theorem that we've discussed. Because on the right-hand side, so you start with a function f, right? So the Fourier transform is supported in S. So by Poincaré, you can think of the right-hand side, you can write the right-hand side in terms of the Fourier transform L2 norm over S. So you start with a function over S, you take the Fourier transform, now it's in the whole space, and you take its L2 norm. So it's just the dual of the restriction estimates that we've discussed. Okay? So why does this contain a built-in uncertainty principle? Okay, it's very direct. Suppose that S is generic, but here, maybe I should say it this way. S doesn't have to be generic. S just has to be a set for which Bourgain's theorem holds. Sorry. Oh, here generic means that it's randomly chosen. So you choose a set randomly by choosing each point with probability alpha. Let's not use p, right? And so that the expected size is about the size of s to the n to the power of 2d over q. No, it's not. It's well, that's because S is random. It's just notation, right? S is a generic set. So what he proved is right. So you can express it in probabilistic language, or you can simply, since we are in a finite setting,
for ends.
Right. Well, it holds for a generic set, and what it means that it holds for a generic set is that if you choose a set at random, then it will hold with high probability. The probability is roughly 1 minus, and there's an exponential tail. Yeah. So it is a probabilistic statement. But what I wrote there, suppose that S is generic. Really, for what you're about to see, you just need to know that that estimate holds. And by the way, the theory of lambda Q sets was originally laid down by Walter Rudin in the early 60s, okay, late 50s, early 60s. Okay, so suppose that F is supported in E and F hat is supported in F. Then Bourgain's theorem implies the following. So what did we do here? We restrict the sum to E because we are assuming that F is supported in E. We took out n to the minus d over q. We brought in 1 over the size of E inside and compensated by the size of E to the 1 over Q outside. Okay, so we just performed elementary school algebra on this side. And we did the same thing to the right-hand side. And now what is the idea? The idea is we are going to put all all the powers of the size of E on the right-hand side and all the powers of the size of N on the left-hand side. And we're going to use a deep fact that the L2 norm, weighted L2 norm, is bounded by the weighted LQ norm if Q is bigger than 2. Okay? And what you get is just this. That the size of E is bounded from below by n to the d divided by Bourgain's constant, or whatever constant you get in that inequality, raised to the power of 1 over 1/2 minus 1 over q. So you need q bigger than 2. Okay? So what this says is that if you have a signal and its Fourier transform is supported on a generic set of size n to the d minus epsilon, then the support of F is a positive proportion of the whole space. Okay? So this blows away the previous uncertainty principles that you have seen. Okay? So one thing that I don't have time to discuss is that there is a rather interesting case which is still work in progress. You want to be able to draw the same conclusion if the Fourier transform is not just supported on on a generic set of size n to the d minus epsilon. But let's say in the generic set of size n to the d over log n. Okay, and this paper is currently being written. Okay, so let me stop there.